So what's going on in our course is that we're hitting like more of the miscellaneous topics and we're slowing down. Okay? We've covered the biggest things that I wanted to cover. So now we need to cover one last abstract thing, which is rings, chapter 16. And then chapter 8, we go back to another application of error correcting codes. So the stuff with rings is going to be easier proofs or computational stuff more than groups. Okay. And then the chapter 8 stuff will be more computational stuff. So I've done this intentionally because I knew that some people would fall behind. So there's time to catch up because the content is slowing down. Okay. Now let's look at chapter 16. So rings. Oh, yeah. So rings are sets with two operations, right? And 1 through 4, so of those things you memorized, 1 through 4 is that addition gives an abelian group. 5 is that multiplication. Is associative. And 6 is that addition and multiplication play nicely. Okay. And if this makes you think of numbers, then yes. Okay. So all the different number systems we've used in mathematics, the integers, the rationals, the real numbers, complex numbers, these are all rings. With traditional addition and multiplication. Okay? Something is not a ring, it's just the natural numbers. Okay? Now, there's other things that are rings that are not just numbers. So for instance, the 2 by 2 matrices with real coefficients is a ring, right? And the addition and multiplication are just the addition and multiplication. So you got your A, B, C, D plus E, F, G, H is component wise A plus E, B plus F, C plus G, D plus H. And then multiplication can be weird. So then A, B, C, D times E, F, G, H equals matrix multiplication goes like that and that. So then AE plus BG, and then row column CE plus DG, then row column AF plus BH, row column CF plus DH. So the 2 by 2 matrices are in some sense a great this is a great example of a ring. Okay? It's a great example for a few reasons. Addition is basically the same as what it's always been. Okay, so anytime in mathematics, when you had an addition symbol and you're adding things that might not be numbers, what you were doing was addition in a ring. Okay, like in calculus 1, when we added functions instead of numbers, we were adding in a ring. Okay, and the other great reason that these are a great example is that multiplication can be weird. Okay, so for instance, in numbers, you can have, if you have like, so in like the real numbers, you have a times b equals 0, then a equals 0 or b equals 0. And you have division, which is basically like multiplying by inverse. So this is true in the real numbers. It's not true in the 2 by 2 matrices. Okay? So in 2 by 2 matrices, you can multiply 0, 1, 0, 0 times itself, 0, 1, 0, 0, and get the 0 matrix. Okay? So you can have two non-zero things and multiply them to get 0. And you can have things that don't have multiplicative inverse. 0, 1, 0, 0 inverse doesn't exist. So you can have no concept of division with 2 by 2 matrices because not everything has a multiplicative inverse. Okay? So that makes it a better, like when you try to think of when you're trying to do a proof of rings or something like that, this is a better example to have in your head. Like, would I be able to do this with 2 by 2 matrices? No. Then it's probably not something I'm allowed to do with rings. Okay? Let's see. So another example of rings is, remember in calculus? So in calculus, we defined like if you had two functions, from the real numbers to the real numbers, then we defined like f plus g of x equals f of x plus g of x. And we never really pointed this out to you in calculus because we didn't want to confuse the engineers. But what's going on here is that these are different addition symbols. This is addition of functions, and it's defined by addition of numbers. And then similarly, you do the multiplication of functions. Multiplication of the functions defined in terms of multiplication of the numbers. So oftentimes we build more complicated rings using like numbers as a starting point. And so, for instance, we build 2 by 2 matrices are built off of numbers, but they're a new thing. That's also a ring in itself. And the space of functions is the set of all these functions from real numbers to real numbers is defined in terms of numbers. It's like built off of numbers. So like numbers are usually our starting point. We create other things that have the same properties as numbers or similar properties as numbers, and they're rings. Okay. I forgot to look up why we call them rings, but it's the fault of some country in Europe, and I can't remember which one. So groups, the reason we call them groups is because of the French. But rings, I can't remember. It might be the French, probably the French, because a lot of like the way this came about was a lot because of Galois. And so I remember he was the guy who died in the duel. So it's weird to call things that we call these things groups, like it's because there's so many other things in real life that are called groups that are not mathematical groups. And it's weird that we call these things rings when like real life there's real things called rings that are totally different. And it's because of its translation error, basically. Not translation error, but it's just like because we're translating it from the country where it was like developed. So neither groups nor rings were really English speaking developed stuff. And we just kind of like used the language of the people who developed it, basically. And that's why we have weird names for these. Okay. And that's just the way it is now. In all over the world, when people do abstract algebra, no matter if you're in like Australia or China or Russia or Sudan, when you do groups, you do groups. When you do rings, you do rings. We've all agreed now. So so it's just the way it is. Let's see. So that's okay. Now you can make weird groups. Another weird group you can make is quaternions. So you remember we had this group we called Q8, the quaternions, which was like 1 and -1 and I and -I and J and -J and K and -K. Let's see, what is the book has a name for the quaternions, I think. H. Yeah. So we use Blackboard Bold H for the quaternions because they were developed by a guy named Hamilton, not Alexander Hamilton, a different Hamilton from Ireland. Hamilton from Ireland. He's the one who developed the quaternions, so we use the fancy H in his honor. And so they're just like it's equal to all real, like a real number plus a real number times I plus a real number times J. I'll use capital letters so that we're same as above. Real number times I, real number times J, and real number times K for A, B, C, D, and real numbers. So then when you multiply two things from the quaternions, so like let's say alpha equals A plus BI plus CJ plus DK, and we'll have beta is equal to X plus YI plus ZJ plus WK. Then alpha times beta is just this really awful computation where you FOIL, but for 4 things and 4 things, right? So then it's like so then remember that I to J to K to I. So if you're going I times J is K, K times I is J. If you go in the opposite order, I times K, you get -J. That's kind of the way to do it. and then anything times itself is -1. Any of the I, j, or k times itself is -1. So then you just FOIL and simplify according to those rules. What the heck? I'll try to do it. So AX plus AYI plus AZJ plus AWK, and then plus B. I'm gonna put them in different order just to try to keep track of everything. Well, I'll just put them in the same order and then we'll figure things out. BXI plus BYI squared. I'm gonna do all the simplification in the next step. Plus BZIJ plus BWIK plus CXJ plus CYJI plus CZJ squared plus CWJK plus DXK plus DYKI plus DZKJ plus DWK squared. Oofta. Then we gotta simplify everything. This is why Sage is so beautiful, because you can do computations with quaternions in Sage and it's no big deal at all. So this is equal to. Let's just you guys are both writing on paper, so I'm gonna do it the hard way up here. All right, so AX plus the whole first line I'm just copying or repeating, plus AZJ plus AWK plus BXI plus BY, I squared is -1, plus BZ, I times J is K, because we're going around the circle the correct way. And then plus AW, but BW, sorry. BW, I times K, that's going backwards, so you get -J. And then CXJ plus CY, CYJI is going backwards, so it's -K, plus CZ, that's J squared, so it's -1, plus CW is JK, so it's +I, plus DXK plus DY, KI is in the clockwise, so that's +J, plus DZ, DZ is KJ, so that's -I, plus DW times -1. And then finally, you write it as the diagonal here is all real numbers. So AX minus BY minus CZ minus DW plus, let's find all the things with I. AY, BX, CW minus DZ. So I'll go in order of row 1, row 2, row 3, row 4. So AY plus BX plus CW minus DZ times I. And then we'll go same for J's. We'll go row 1, row 2, row 3. So plus AZ minus BW minus BW plus CX plus DY. And then I'm running out of space. I'll do the K's. So the K's are AW plus BZ minus CY plus DW. No, DX. Okay. Right? So notice like once you do all your simplifications with IJs and Ks, it's all built on real numbers. It just has weird things that give it a special structure. So this is a ring that has division in it to it, because every non-zero element has an inverse. But it's not commutative like numbers are normally. Multiplying different left and right gives you different elements. So it's another good example to have in your back pocket, even if it's just awful to compute with. Okay. So I think the book has this proposition and this proposition. Okay. So let's put this in here. Okay. So when you're proving stuff with arbitrary rings, you need to kind of view the fact that symbols like zero, addition, and multiplication, and even one are contextual. They can mean different things for different rings. So for instance, the zero of the 2 by 2 matrices is the zero matrix. Okay. And the 1 of the 2 by 2 matrices is the identity matrix. Okay. So when we refer to the zero of the ring, what we mean is the identity under the addition operation. And by the 1, we mean the identity under the multiplication operation. So the thing that's always true, 0 is always the identity. Identity with respect to addition. 1 is always, and sometimes you might have like a sub, like the little R there, just to show like, this is the 0 with regard to my ring, but it might not be like a number 0. That makes sense? It's always the identity of multiplication. And so in this proposition here, there's zeros and there's negative signs. So what does a negative sign mean? It means the additive inverse. So minus always means additive inverse. Okay, so with that in mind, let's look at a proof here of 1. So let A be an element of a ring. Okay. Then let's see. The way these proofs work is that it's generally like a really short, cute thing. Yeah, that's it. So, then A times 0 is equal to, so the only thing you can do is the only thing you know is that 0 is the additive identity. So recall, like, you can only do things like 0 is equal to 0 plus 0. Right? So that equals A times 0 plus A times 0 because you can distribute multiplication. Multiplication and addition work nicely together. They play nicely. Okay? Subtract A0 from both sides. And you get 0 equals A0. Then you just do it for the other side. Similarly, 0 times A equals 0 plus 0 times A equals 0A plus 0A. So subtracting 0A from both sides, 0 equals 0A. And that's it. That's the proof. So what was the trick? The trick was going from 0 to 0 plus 0. Okay. So here, if say you wanted to prove number 2, I'm not going to do the whole proof, but what is it you need to show? Is really, when you like zoom in on this equation, what you're really doing is showing this is equal and this is equal. That's really what you're showing. So what is this thing? It's a product of A and B. So the negative in front of AB means what? The additive inverse of AB. So if x plus AB equals 0, then x equals negative AB. That's what the additive inverse is, right? This is not part of my proof. This is like saying what little this is like a little angel above the shoulder of the proof that says, like, this is what I need to show. So then what do you need to show? You just need to show that like negative A, so the way you start the proof is it is enough to show that negative AB plus AB equals 0, and A times negative B plus AB equals 0. My hint, factor. Okay. So you want to be careful because multiplication doesn't have to be commutative. So you can't swap the order of multiplication, but you can factor out to one side or the other. Okay. All right. So then rings subrings. Okay. So a subring is a subset that is a ring under its own right. Now, if there's an element one, such that one, yeah, there's lots of definitions up there that we'll get to later. Okay, so kind of, do you remember how we had that proof that kind of made it simpler to prove when there's a subgroup? Do you remember from our subgroup section? And we said we defined what a subgroup was. It's like a subgroup's a subset that's a group in its own right. And then said, well, here's this proposition. Here's what you actually need to prove. You got to prove it includes the identity. Inverses are included in the set, and the set is closed under multiplication, the group operation. Okay, that's basically the same thing as what's going on here. Okay, so like R minus S, that's like do you remember that other theorem that said, well, as long as the subset is non-empty, we did this one we did on the board up in the back. As long as the subset is non-empty and GH inverse is in there, then it's a subring or subgroup. Well, R minus S, remember addition is an abelian group. So you're just doing that. That's going with that operation. And then also like it's closed under multiplication. So it's just like the same as subgroups, but with one extra step. Because you got an extra operation. So for number 2, you're showing it's closed under multiplication. Number 3, you're showing it's still a subgroup under addition. Okay? Because remember with rings, multiplication can be weird, but addition is always like addition, which means it has a structure of a abelian group. Okay? So that's all there is to it. So for instance, here's an example showing like the upper triangular matrices are a subring of the 2x2 matrices. So if you have two upper triangular matrices, A and B, then if you subtract A minus B, it's going to be upper triangular. And if you multiply them, you get this as upper triangular. So, and then it's not empty because there's stuff in there. So it's a subring. That's all you got to do to show it's a subring. Okay? Okay. What is the homework I assigned for this section? Okay. So there's the 1 ABCE, just ring, and then 17 and 27 just subring. Okay. So you don't have to prove for number one. Okay? You just have to figure out like whether or not they're rings. Okay? What are the things that can go wrong with something not being a ring? Um, something that could go wrong is if you multiply two things together and it gets outside the ring, or if you add two things together and it gets outside the ring. And so I'm just going to tell you most of these are rings. There's either one, two, or three that are not. Okay? So you might need to think about how all of these sets are in the numbers, except for like Z18. And so all these sets are in the what we think of as the numbers. And so, but they're subsets. And so is it possible to like multiply two things and get outside the subset? That's going to be your main question. Okay. And then 17 and 27. Yeah, so I said just rings. Yep. We're learning about fields next time. Mhm. Okay. And then 17. Wait, that doesn't seem right. No, 17 and then 27 just subring. Okay. So 17 is a lot like that proof. I a lot like that proof with the zero. But it's more of the fact of like, how do you show that this is true? You take this thing and add it to just A and see if you get zero. So for 17, I want to show -1 times A equals negative A, which is, this is a thing where when you first see this and you're asked to prove it, you're like, duh. Okay? But you have to remember what each of these things means. So -1 is the additive inverse of 1. -1 is a thing that when you add it to 1, you get 0. So for instance, in like, use your example. Like in the 2 by 2 matrices, -1 is really -1, 0, 0, -1. It's a thing that when I add it to the multiplicative identity, I get 1 or 0. Okay? So you want to show this. So then in your proof, you can say it is enough to show -1 times A plus A equals 0. And the way you're going to prove it is by doing something so that you can factor out A. That's my hint. Okay. And then let's look at 27. 27. Let R be a commutative ring, and the element of A in R is nilpotent if to the power of n you get 0 for some positive integer. So instead of ideal, we'll do subring. So show that it's a subring. So then what you need to do for 27 then you might want to name it. Maybe capital N equals A in the in the ring such that A to the N equals 0 for some natural number. Show it's a subring. So you got to show three things. One, it's not empty. Show that N contains at least one thing. What do you think that one thing's going to be? Yeah. All right. Now, you got to show that you got two nilpotent things. Then AB is nilpotent. Okay.
You should think of that one as a subring.
What's that?
You should think of this one as a subring.
We're going to prove it's a
Or
subring.
prove it as a
Yep.
subring.
And then 3 is you got A, B, and N. Then A minus B is an N. So those ones, so the part 1 is the easiest one. Now, R is a commutative ring. What does that, do you guys know what that means? Do you remember what that means? So commutative means multiplication works like that. Okay? So with rings, remember that addition is your group operation and multiplication is weird. So when it's a commutative ring, that means your multiplication is also has that like a Booleanish property to it. Okay? So that means that when you take like AB to a power, you can just do A to the K, B to the K, because commutative. Does that make sense? Because AB to the K, if it wasn't commutative, it would be AB, 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 AB. Right? AB to the K means AB, K times. But since it's commutative, you can just push all the A's to the left, all the B's to the right, and you get A to the K, B to the K. Okay? So that's a pretty simple proof for number 2. Once you understand what you're trying to prove, it's quite short and sweet. And then similarly, like when you do A minus B to the K, then so you want to show that like if A is nilpotent and B is nilpotent, then A minus B is nilpotent. So you want to find like some power that sends this thing to 0. And So are you guys familiar with the binomial theorem? Okay. So this is the thing you're going to need. By the binomial theorem, a minus b to the k is going to equal sum, and we can use summation notation because it's a ring, all right? Of I equals 0 to k of, do you remember this notation? Like k choose I. Remember that at all from discrete math? We could still do it with rings because k and I are integers. Okay? Times a to the I times negative b to the k minus I. Okay. So you're going to need the power of k that's big enough that you're either annihilating the a's or you're annihilating the b's. Make sense? So what does it mean to be nilpotent? It means like there's some power that when you take it to itself, you get 0. So for instance, let me give you an example of nilpotent stuff. So in the 2x2 matrices, 0, 1, 0, 0 is nilpotent. Because 0, 1, 0, 0 squared equals, when you do like row, column, 0, row, column, 0, row, column, 0, row, column, 0. Yeah, so nilpotent, it's nilpotent if there exists a power such that you can send it to 0. So for instance, in like the real numbers or any number system, nothing's nilpotent except 0. So the number systems are not a good example, but the rings, the 2x2 matrices are a great example because they have other nilpotent elements. Okay, and then 0, 0, 1, 0 is also nilpotent. When you square it, you get 0, 0, 0, 0. Okay, but then what if I take one minus the other? So that's A, this is B, so then A minus B equals 0, 1, negative 1, 0. Okay, now I'm just going to compute here and see what happens. I square that. So then A minus B squared equals 0, 1, negative 1, 0 squared equals row column is negative 1, row column hold on, row column is negative 1. Oh dear. Oh, this doesn't work because it's not commutative though. So this property, this theorem doesn't apply here because the 2x2 matrices are not commutative. So it doesn't work. Upper triangular matrices are commutative. So it would work if you only stayed with the upper things there. So for instance, like 0, 5, 0, 0 is a nilpotent element minus 0,700 is equal to 0, -200, also nilpotent. Okay. So a key thing for this proof is that is you need the binomial theorem, and when you forget about this example now, because you don't want to you want to actually prove it. The example is just like to get your mind around it. Okay. So when you say in your proof that let A and B in the nilpotent elements, the next thing you say is then there exists N and M in the natural numbers such that A to the N equals 0 and B to the M equals 0. That's what it means to be nilpotent. So then you want to do, so then A minus B, and you're going to want to pick something here, equals, then by the binomial theorem, then by the binomial theorem, A minus B to a certain power is equal to the sum I equals 0 to that power of that power, choose I, times A to the I times negative B to that thing minus I. And you want to choose that number big enough so that every single term becomes 0. Okay, that's how your proof is going to work. All right, now that's all we have to say about rings. So feel free to get started.